In today's video, we shall take a closer look at Newton's second law of motion. As we have seen in our previous video, Newton's second law relates net force acting on an object to the acceleration of that object. So if an object is being subjected to, let's say, many forces, let's call these forces F1, F2, F3, and F4, realizing all these forces are vectors, then the net force acting on this particular object is quite simply vector sum of all the four forces, in this case F1 plus F2 plus F3 plus F4. Thus, applying F equals to ma to a particular problem involves two crucial steps. The first step is determining the net force in this following way. And step 2 is to equate that net force to ma. While these steps may seem straightforward, applying them to problems may get a little bit tricky depending on the problems. To this end, let's look at some of the examples and see how we can apply F equals to ma to these problems. The first one is the very simple problem of an object moving under the influence of gravitational field. Now let's assume that the mass of the object is m. We know it falls under the gravitational field. What are the forces acting on this object? Well, there is only one, and that force is its weight, mg. We also know, since it is falling under the influence of gravitational field, the acceleration is a, pointing downward. So step 1 is determining the net force. The net force is, from this free body diagram, the weight, and that is just mg. So that is step 1. Step 2, equating this net force to ma, where a is the acceleration of this object. So that is step 2. The outcome from the simple analysis is, by equating these two terms, you see that the acceleration of this object is just the gravitational acceleration, which is 9.81 meter per second squared. In this example, F equals to ma reveals another important concept. This is namely the difference between the weight and the mass. Now the weight is a type of force, so it's quantified in the units of newtons. Mass is a scalar, and it's quantified in the units of kg. So there you go. Difference 1, weight is a vector, mass is a scalar. The second point about these two quantities is that weight can change, whereas mass of an object cannot change. What do we mean by that? If we were to repeat this experiment, where an object is falling in a gravitational field, but instead it's following in a gravitational field of, say, Moon, where the gravitational attraction on the surface of the Moon is 1/6 the gravitational attraction on the surface of the Earth. So in this case, the weight of the very same object on Moon will be the mass of the object on Moon, which is the same as the mass of the object anywhere, times the gravitational attraction on the surface of the Moon, which is 1/6 the gravitational attraction on Earth. So that means it's 1/6 the weight of that object on Earth. Now let's see how to apply F equals to ma for an object moving on an inclined plane. So let's say the mass of the object is m. The angle of inclination is alpha. Let's call that alpha 30 degrees. Let's assume we want to determine the acceleration of this object down the plane. What is it? We know the object is acted upon by its own weight, m times gravitational acceleration, 9.81, And of course you have a normal force from the surface of the plane acting upward on that object. Because the direction of the normal force and the direction of acceleration along the plane is 90 degrees with respect to each other, the normal force will not affect acceleration unless there is friction between the surface of the object and the plane. So in this case, we neglect such friction. So let's for the moment neglect that normal force as well. Let's not show it on our diagram, but we know it's there. So how do we determine the acceleration a? How do we apply F equals to ma to this simple object? The first thing to realize is that this weight, since it is a vector, it has two components. The first component is component parallel to that inclined plane. Let's call it W parallel. The other component of that weight is perpendicular to that plane. Let's call it W perpendicular. It is this component that is causing that acceleration. So the net force acting on this mass along the plane is W parallel. So let's just concentrate on that W parallel. What is it in terms of mg? Note that since the angle between the horizontal and the plane is 30 degrees, we can sort of create that geometry and figure out that is indeed 30 degrees as well. What that means is this is 60 degrees. Now let's look at W parallel and make a triangle with mg as the hypotenuse of that right angle triangle. So this is a right angle triangle. So what do you have essentially? It's a right angle triangle, 90 degrees here, 60 degrees there, so that must be 30 degrees. This is W parallel and that is mg. So you see W parallel over mg is quite simply sine 30 degrees. So that means W parallel equals mg sine 30 degrees. So there we have it. The net force acting on that object is mg sine 30 degrees. And according to Newton's second law, the net force equals ma, where a is that a. So by equating ma to mg sine 30, you see that acceleration a is g sine 30 degrees. So that is the acceleration of this object as it slides down that frictionless inclined plane. So you see how we have applied Newton's second law with two steps in solving this problem. Let's look at the following problem. A small ball of mass 2 times 10 to the power minus 3 kg suspended from a cord. A steady horizontal breeze pushes the ball so that the cord makes an angle of 35 degrees with vertical. So alpha here is 35 degrees. Find the force from that push and the tension in the cord. So let's look at all the forces acting on this ball. One is of course its weight, and we know it is 2 times 10 to the power minus 3 kg times gravitational acceleration. The other one is the horizontal push from that breeze, let's call it F. And the third force is the tension in the cord, let's call it T. The ball is not moving because the cord always makes an angle of 35 degrees with vertical. Alpha is always 35 degrees. So that means it's stationary, then the acceleration is 0. What that means is the net force, according to Newton's second law, has got to be 0 in all directions. This is a two-dimensional problem. If you take that direction to be x and that direction to be y, then the net force along the y direction is 0. The net force along the x direction is also 0. So let's look along the y direction first. So this angle here is alpha, and alpha is 35 degrees. Now there are two forces acting along the y direction. One is the weight, and the other one is the y component of that tension. So the y component of the tension equals weight, which is 2 times 10 to the power minus 3 times gravity. Now the y component of tension in terms of t and 35 degrees is t cosine of alpha, or cosine of 35 degrees, and that is 2 times 10 to the power minus 3g. We arrive at this conclusion using the fact that net force along the y direction is 0. So the acceleration is 0, which gives us this line. So let's call that equation 1. The second equation is by considering the net force along the x direction to be 0. So that means the horizontal F that we want to find equals the x component of the tension. So the x component of the tension is T times cosine of that angle or sine of that angle. So sine of 35 degrees. So that is equation 2. We can solve the tension from equation 1. So from equation 1, tension is 2 times 10 to the power minus 3 times g over cosine 35 degrees. And that's going to give you 0.024 newtons for the tension. Substituting that value of tension that we have just found in here, you can get that horizontal push. So that is 0.024 times sine 35 degrees, which will give you 0.014 newtons. And that solves the problem. Problem 2. A 55 kg person is to slide down a rope that will break if the tension exceeds 450 newtons. What happens if the person hangs stationary on the rope, and at what acceleration does the person just avoid breaking the rope? So let's look at part A. If the person is just hanging there, this is just a schematic diagram, then the forces would be the weight of that person and the tension upward. So in this case, the tension will be mg, the weight of the person, so 55 times gravity, which is about 540 newtons. Since this is greater than 450 newtons, what's going to happen in part A? If the person is stationary, that rope breaks. Now part B. Let's assume the person is moving, namely, the person is sliding down with some acceleration a. At what acceleration does the person just avoid breaking the rope? So again, you have tension, and if just avoid means the tension at that point is 450 newtons. And of course, the person has the weight of 55 times gravity. So let's first work out the net force. The net force is downward, and that is 55 times gravity, the weight that is, minus the 450 newtons of threshold tension. According to Newton's second law, that must be ma. M is 55 kg times a. Equating the two, you should be able to figure out the acceleration. Doing the calculation, you'll get acceleration to be 1.63 meter per second squared. So at that acceleration, the person just avoids breaking the rope. And that solves the problem. If you find this video useful, please consider subscribing to this channel for more videos to come. As always, thank you for watching.